So today we're going to talk about the law of conservation of energy using a vector calculus approach. We're going to cover a few topics. The first one is the derivation of kinetic energy and potential energy using vector calculus. We'll then use these concepts to derive the law of conservation of energy, give you an example of the law of conservation of energy at work, and then discuss the limits of law of conservation of energy. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time. So remember this concept of isolated systems because we'll come back to that at the end of this talk. And energy can neither be created nor destroyed. Rather, it can only be transformed or transferred from one form to another. Essentially, the law states that the kinetic energy, the sum of the kinetic energy plus the potential energy at point A is equal to the kinetic energy plus the potential energy at point B. And it's denoted as this. PA is the potential energy at A plus KA, kinetic energy at A, is equal to PB plus KB. Before we move on to actually deriving kinetic energy and potential energy, I need to go through some definitions to set the stage. Newton's second law of motion describes the relationship between the motion of an object and the forces acting on it and can be paraphrased as follows. At any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass. So essentially, force is equal to mass times acceleration. And in vector calculus terms, it is force field is equal to mass times the acceleration vector. Okay? So remember that formula, and then we'll move on to some other definitions. Kinetic energy of an object is the form of energy that it possesses due to its motion. So the kinetic energy of a non-rotating object of mass m traveling at speed v is half mv squared. Remember that formula, kinetic energy is equal to half mv squared. Potential energy, on the other hand, assuming the force is conservative, and I'll just define this term later on, the relationship between force and potential energy is that the force is equal to the negative gradient of the potential, where P is the potential analogous to potential energy. So F is equal to the negative gradient of P. Now we're going to move on to the derivation of kinetic energy, and it all starts out with work, right? We always go back to work done by a force on an object. So work here is the line integral over a vector field F along a smooth curve C. And this gives us the dot product of the force field, F RT, with the velocity vector R prime T over the interval A to B. And this force field here is replaced by the Newton's law of second motion by m times the acceleration vector dotted with the velocity vector. Now here, notice that we have the acceleration vector as well as the velocity vector. And we remember that kinetic energy was half mv squared. So we need to bring this back in terms of the velocity vector. So we're going to do some manipulation there. This essentially is a calculation in reverse. What I'm going to do in the end is substitute this entity with this entity. But I'll go through the derivation in reverse and show you why it works. Assuming that we have an equation which is half the derivative of r prime t dotted with r prime t. So velocity vector times velocity vector. When you apply the product rule of differentiation, you get half velocity vector times, acceleration vector times velocity vector plus velocity vector times acceleration vector. These two are the same. That becomes 2 times acceleration vector times velocity vector. The 2 and 2 cancel out, and you get r prime t dotted with r prime t, r double prime t dotted with r prime t. So acceleration vector times the velocity vector. Now you notice that this is the same as this, and in the next slide, I'm going to substitute this entity with this entity here. So we left off over here where we had, when we applied the Newton's law of Newton's law of motion, second law of motion. And now we're going to, as we said in the last slide, we replace this entity here with this over here. And the reason why we do this becomes clear in a moment. But first I want to go over a couple of other concepts here. Remember that the fundamental theorem of calculus 2, we find the antiderivative and then evaluate at the limits of integration. That's the fundamental theorem of calculus. And also another concept where you take the magnitude or the norm of a vector is equal to the square root of the dot product of the vector. So when you square this, you get u times u, or u dot u, okay? So those two concepts are going to be applied in this step over here, where you have this equation over here, you apply the fundamental theorem of calculus, and you get the antiderivative, and you use the u dot u concept, and you get the norm of the velocity vector. So a lot happening in this step, but hopefully that's clear to you right now. So you get the sum, so you get this equation over here, which is m over 2, the square root of the norm of the velocity vector integrated from a to b. And that simplifies to this over here, which is now beginning to look very similar to the kinetic energy equation, which is that basically it is m over 2, the difference between the velocities at point A and point B. So that simplifies to this equation over here. Essentially, the work in a force field moving a mass from point B to point A is essentially the difference in the kinetic energy at these points. Okay, so we've derived the kinetic energy and we're moving on to now potential energy. But before we do that, I need to go over the fundamental theorem of line integrals with you. This theorem states that let C be a smooth curve given by a vector function, RT. Let f be a differentiable function of 2 or 3 variables whose gradient vector del f is continuous on C, then you get this equation over here. And essentially the theorem says that we can evaluate the line integral of a conservative vector field, the gradient vector field of a potential function f, simply by the value of the function at the endpoints A and B. In fact, the theorem says that the line integral is a net change in the function. So that's what this integral is. That's what this theorem is saying, and we're going to use that concept in the next slide. But first, once again, definition of potential energy. Forces derivable from a potential are also called conservative forces. So they're path-independent forces. The work done by a conservative force is equal to negative del P, where P is the potential, which is analogous to potential energy. The negative sign provides the convention that the work done against the force field increases the potential energy. So we multiply the line integral by -1 to get the work performed against the force field. So that's why we have this. This is by convention that force is equal to the negative gradient of the potential. once again, everything, like I said, comes down to determining what the work done is. And as you remember from the last slide, the work is the line integral of the vector field F along a smooth curve C. Okay? And in this case, we apply the fundamental law of line integrals. So the force can be, because it's a conservative force, the F is a conservative vector field, and therefore it's the gradient of the potential function here. So we apply the gradient of the potential. Remember, there's a negative sign over here. And then essentially the fundamental law of line integral says that is the net change in the potential from point B to point A. And when you distribute this negative sign over, it becomes PA is equal to minus PB as the work done for potential energy. Now, we've got the potential energy and as well as the kinetic energy. I'm going to combine these two things together in the next slide. We're almost home. Let's finish this. The law of conservation of energy now, remember that the potential energy we derived was work is equal to PA minus PB. Kinetic energy was work is equal to KB minus KA. When you combine these two together and distribute the like terms on the right-hand side and the left-hand side, you get PA plus KA is equal to PB plus KB. So that, in a nutshell, is the law of conservation of energy. Some aspects of this, it essentially says that if an object moves from one point to another under the influence of a conservative force field, which is path independent, then the sum of its potential energy and its kinetic energy remains constant. This is called the law of conservation energy, and it is the reason why the vector field is called conservative. Some aspects of the conservation of energy, again, as we said before, it may change in form or be transferred from one system to another, but the total remains the same. And some commonly encountered forms of energy include electrical energy, chemical energy, radiant energy from the sun, nuclear energy, mechanical energy, and thermal energy. So for example, some energy transformations are, if you eat your ice cream and then go for a bike ride, the chemical reaction of digesting your ice cream is then transferred to a mechanical energy of riding a bike. Or, for example, the sun, which transmits radiant energy, is converted by plants into chemical energy in the form of photosynthesis. Or, for example, you fill up your car with gas. The chemical reaction of the gasoline combustion is then transferred into you driving a car in the form of mechanical energy. And finally, if you're cooking a meal at home, the electrical energy from the plug is converted into thermal energy, and you frying an egg in a pan. So now we're going to go over an illustration of conservation of energy, and that is essentially swinging a pendulum and marking its positions. The extreme ends of the movement are A and B, and the midpoint C. And the next slide has a lot of information, but I'll go through it very slowly. Essentially, it is describing the swinging of a pendulum and conversion of kinetic energy to potential energy and vice versa. So for example, the ball is pulled to A from C. The kinetic energy from our hand is converted into potential energy and is transferred to the ball. At point A, the potential energy is the maximum and the kinetic energy is 0. Now the ball moves from A to C, converting the potential energy to kinetic energy. From C, where the potential energy is 0 and kinetic energy is at the maximum, the ball keeps moving because of its kinetic energy, moves to point B, where At point B, the kinetic energy is converted into potential energy. As a result, the potential energy is the maximum, kinetic energy is 0. The ball pauses momentarily at B and then starts moving back into the opposite direction, and so on. It moves to C, moves to A, and then to C, and then to B. So at points A and B, the potential energy is the maximum. There's no kinetic energy. At point C, it's maximum kinetic energy. So this shows you the conversion of potential energy and kinetic energy and vice versa. And eventually the ball collides with air molecules and loses its kinetic energy and potential energy to air molecules, and then will eventually come to rest. All right. So here are then the limitations of the conservation of energy. In contrast, so if we were in outer space where there is no atmosphere, there would be no collision between the balls and the air molecule, and therefore there would be no loss of potential energy and kinetic energy, and the swinging process would continue on forever. So the swinging of the ball in outer space behaves like an isolated system following the boundaries of law of conservation of energy. So that is an isolated system. On Earth, we're not an isolated system. So we're coming to the home stretch here, which is the conclusion of our talk over here. We've used vector calculus to derive kinetic energy and potential energy. I hope if you're still watching, which I hope you are, I hope you've enjoyed this demonstration of how vector calculus can be used to derive these very well-known formulas to us, which is kinetic energy and potential energy. It was eye-opening to me how that worked. We then used those concepts to derive the law of conservation of energy. We showed a classic example of the law of conservation of energy, which is that swinging pendulum. And then finally, we discussed the limitations of law of conservation of energy in this talk. So as I finish up, I'd like to leave you with a slide with a photo of the 2024 solar eclipse and a photograph taken by Peter Leva showing our radiant sun. Thank you for watching, and I hope to see you in the next video.